popular qubit now in the community, right? So what is that? Now, we have been working on Cooper pair box, and I only limit it to 2 levels, and that's why we had this equation, when we limit it to 2 levels. And these 2 levels are n equal to 0 and n equal to 1. Right? So I actually have a code, Python code, that you can download from GitHub, right? Look at the book. Then you can try to solve it for many levels. The basis, as I told you, right? The solution, the accurate solution should be for n equal to negative infinity all the way to n equal to positive infinity. But numerically, you just do 100 will be good enough. So you try to solve it, and what do you see here? On the left, we have the ECC, which is much larger than EJ. And this is the so-called charge qubit. And needless to say, right, when the charge Ng change, when it is half, right, this is, why? When it's half, then you have a certain energy. But the point is, if I change this a little bit, right, let me just redo this. For example, the charge, let's say it changed from, it's difficult to do. And I'm sorry, this is not really, this is actually state 0. So let me say again, this is the ground state, and then this one is the excited state, but this is the excited state minus the ground state energy. And this is the second excited state. So what we are showing here is that I make all the ground state same, right? So I have a reference. They are actually not constant, but I just make them constant. But then I adjust the rest, because what I'm plotting is actually difference between 0 to 0. So of course 0 to 0 is constant, right? And then difference between 1 to 0. Difference between 2 to 0. Is that okay? So E10 is the qubit energy, right? So again, as I told you earlier, this is the sweet spot, Ng equal to half. If I have any charge noise from here to here, you see that the energy would change a lot. Do you see that? This is the charge noise. If I move the Ng from this point to this point, the orange change a lot, right? Energy change from here to here. Make sense? And this is the qubit energy. So this is very sensitive to charge noise, charge qubit, right? This is sensitive to delta Ng, which is charge noise. Now, if you solve this one for another case, which is ECC much smaller than EJ, ECC smaller than EJ, this is called a Transmon Qubit. What do you see for E10 when I have charge noise? It's constant, right? So this is insensitive to charge noise, right? Even then, better than at the sweet spot. Okay, that's first thing. Second thing is a little bit confusing, not confusing. Again, what are the ground state of this? They are eigenstates. As we said, right, they might be plus and minus. But the eigenstate of this guy, of the Transmon Qubit, we did not show it, but we can show in the book. We will not prove it. Turn out to be capital N equal to 0, capital N equal to 1, and capital N equal to 1. So it behave like a LC tank or a simple harmonic oscillator. So the state, although we are talking about ground state, they are both ground state and excited state. This one's ground state, let's say at the sweet spot, not outside because it's very complicated, but at the sweet spot, I better say it's sweet spot so you won't get confused. In the sweet spot, the eigenstate is plus minus, right? Which is the superposition of n equal to 0 and n equal to 1, but n is small n. That is the number of Cooper pairs. Here we have capital N equal to 1, which is the n of a simple harmonic oscillator. So here you won't get negative 1, negative 2. You must start from 0, 1, 2, 3, 4, 5. Right? So that is the distinction between a Transmon qubit and a charge qubit at sweet spot. Is that okay? Then I want to introduce anharmonicity. We never try to do this because in order to find the anharmonicity, we need to solve many levels. Many level means, let's say, multiple level. For example, from small n equal to negative 10 to small n equal to 10. Okay? But anharmonicity means this. You see that earlier for the LC tank, this is LC tank. It has a parabolic energy shape. Then you will get an even spacing of the energy. But now, due to the Josephson junction, this actually becomes a cosine. So this is not parabolic. As a result, the energy difference between the first two levels is different from the next two levels. And alpha, which is defined as E21 minus E12, is the so-called anharmonicity. Right? So if you can have, so in the Transmon, alpha equal to EC. Okay, equal to charging energy, not ECC, equal to EC. Turn out it equals to EC, okay? Now, and we also find that if you increase EC, I should say this, sorry. If, as we say, right, we want the Transmon to have EJ larger than EC, right? So if EJ larger than EJ over EC increase, unfortunately, alpha will decrease. Okay? Although the charge sensitivity will also decrease. And that is the problem or the characteristic of a Transmon. So you do see that it is in when we have the EG over EC is large, you do have a constant or energy, so you are insensitive to charge. But if you compare with the two levels, the energy difference between these two levels, they get smaller. Okay? Look at this charge qubit. The energy difference between E10 and E21 can be very large, right? This is very small, this is very large. The difference is very large, which is good if you want to have a two-level system. But in order to reduce the charge sensitivity, we need to increase the Josephson junction energy. Although it reduces the charge sensitivity, however, it also reduces the anharmonicity. Okay? But luckily, the theory say that charge sensitivity is reduced exponentially. So it means it reduces very fast. While the alpha will reduce algebraically, right? Not algebraically. I mean just square root. Forgot the equation. Okay, reduce as the square root of 1 over square root. Right, so I may be wrong. I may be wrong. I forgot the equation. Right, it might be EC to the power, let's say, negative half. Okay, this is like exponential e to the power EC negative half. Anyway, right, so you need to check my book, I forgot. Right, but anyway, the point is that there's a trade-off, just like any engineering work. Okay, so you increase the Josephson junction energy to bring it to a transmon regime. You are insensitive to charge exponentially, but your anharmonicity also reduces. So this is a trade-off. When you're insensitive to charge, which differential criteria you are helping? Huh? No, I mean insensitive to charge. Which one are you helping? Huh? High coherence time, thank you. Sorry, my ear has problem. And then which one you are hurting for alpha reducing? Yeah, it's not a well-defined level 2 system, right? Because if they are equal spacing, then it's multi-level system. Right? So it's a trade-off. And for charge qubit, it's opposite. We have a very well-defined 2-level system because this energy here is so much smaller than this two. So I am not going to excite to the upper level easily. But it's very sensitive to charge. So the coherence time is small. Okay. So actually, what's that? What? Oh, this is 16. Yeah. So then, here is just some characteristic. We don't prove it here. It's in the book, but it's useful. Always remember. So here I'm wrong. This is negative EC. I say it wrong. Right? What is the meaning of negative? It means the E21 is smaller than E10. So this is usually the case, right? So the alpha for transmon is negative EC. This is the qubit energy, square root 8 EC, EJ minus EC. Remember what is the E01, the qubit frequency of a charged qubit at sweet spot we just talked about? Forgot. What is this? What is the qubit energy? EJ, right? Just the Josephson energy. But this is related to the capacitor also. Capacitance energy, right? That's the first thing. Second thing, I want to show you something. Let me just call this is the qubit energy. So I want to show you, you can also, right? That's just quantum mechanics. You can project, right? This is n equal to 0. Project to the charge basis, right? Or maybe make it clear, n equal to 1, project to the charge basis, which is small n, right? So basically what I do is n and then n equal to 1 for each of them, right? So you see that what is small n again? Small n is the number operator which acts as the momentum, the generalized momentum. So this is just like the wave function projected to the momentum space. It's very similar to, it's the same as the simple harmonic oscillator. You project to the momentum space. The simple harmonic oscillator, you capital N equals 0, capital N equals 1, right? You can project that into momentum space also. Won't test this, right? I challenge you to think about it, really think about it, and talk to me if this is not clear. Right? So this is like n is the eigen function of Transmon. And then phi, right? Let me don't call it phi, just n, small n, is just the momentum eigenvalue. Right? So this is similar to mechanical SHO, simple harmonic oscillator, in which we project the n to p instead of x, but we project to the p space, the momentum space. Okay? Yeah. This one? Yeah. It's just like the number of quantum. So it's 0, 1, 2, 3, 4, 5, 6. We did not prove it, but turned out to be. Yeah. Yeah. Small n, yes. Yeah. Yeah. Capital you can, it's just a quanta of energy. And what is it in terms of the Qubit pair? It is like this. So it is this much of n equal 0 plus this much of n equal 1 plus this much of n equal -1. So it is a superposition. Like this room may be in the Transmon state will be that we have 0.1 extra person plus 0.01 extra 2 person, 0.0 extra chair, right? And then 0.01 one less person, something like that, right? So it is like as messy as this. Okay, so that's a good question. This is the eigenstate. Yeah. Which one? Say again. Oh, the orange one is just the wave function itself, and the blue one is just the square of the wave function. So here represent the probability that you will find 0 Qubit pair if you really try to measure the eigenstate. So you have the largest chance to find that there's no Qubit pair, extra Qubit pair. Here actually you have the largest chance to find, you almost have 0 chance to find 0 Qubit pair, but it has plus minus Qubit pair. Yeah, okay. You cannot, how do you emit this? First, if you design in this way, you see the charging energy larger than Josephson junction energy, then it is a charge qubit. If the Josephson energy is much larger than the charge energy, then it is a transmon. Now, but what is the characteristic is that when you have that system, it turns out that your eigenstate is this capital N. And each of this capital N is like a linear combination of the momentum. Or on the other hand, it's just that the transmon behave like a simple harmonic oscillator. Although I don't know what is the meaning of n equals capital N equals 0 equal 1, but they represent 1 quanta, 0, 2 quanta of energy. When n equals 0, no extra quantum energy. Right? So because it's a simple harmonic oscillator, so its energy is still h bar omega plus half, n plus half. Right? But with some anharmonicity, now we're doing something, we simplify it, right? Only thinking about the first two states. So these are all valid. Yeah. Very good question. Yeah. Now, then how do we do the 1-qubit gate? We are not going to spend time to derive it, right? Because it's too much math. We need to stop here. But again, you just follow exactly the methodology. It is the same circuit. But this time we have an envelope one function, which is s of t. Not just constant v1, but s of t, which is equals to Actually, I did not put it here. Refer to my book. And that's the sine wave. Okay? So you have an envelope function, and then you have the sine wave. You go through the equation. Again, you get sigma c and sigma y. And you know what it is again, right? So this is just like the rapid oscillation, right? So you have this h omega equal to this, and eventually you can also have the cosine phi and q phi. If you try to do a rotating frame and rotating wave approximation, then eventually you get into this equation. And this equation is the same as the chapter 10 where we talk about the rotating magnetic field on the xy plane. If you remember, you will get an equation like this. And then the sigma x, sigma c will give you an effective vector, and then your qubit will rotate about this vector. Okay, so the math will be the same as that one, right? And finally, how do you get a 2-qubit gate? So on the left is a transmon, on the right is also a transmon, right? 2-qubit. You couple it with a capacitor. Okay, now you go through the math, you again have a lot of stuff. I don't want to teach, you can go through, I think I write it very clearly. The point is that you go through the math, you will see that it has a matrix like this. So what you want to do is that before you couple them, they operate separate as 2-qubit with two different qubit frequency. So they won't affect each other. But when I want to have a 2-qubit gate, this is a so-called flux tunable qubit. I will pass some magnetic flux through here, then its Josephson junction, effective Josephson junction energy will change. Once it changes, I bring them into resonance. I bring them for a certain time, which is given by this. I will be able to get this iSWAP gate. And why iSWAP gate? Because any iSWAP gate can be combined with other 1-qubit gates to form a C0 gate. And then you can do 2-qubit gate. So I know I'm a little bit rushed here. I just take a look. I really don't need to go to the math, right? But the math are in the book if you are interested. The message is that Transmon Qubit behave like a simple harmonic oscillator, first thing. Second is charge insensitive. Third, it have a relatively low anharmonicity, which is still good enough. And if you apply a sinusoidal wave with an envelope, you do it right, then it will just like a spin qubit that have a certain rotating magnetic field. The math will be almost the same, right? And you can do the 2-qubit gate, which is iSWAP, the native gate. Remember, the C phase gate was the native gate for the spin qubit, right? But for Transmon Qubit, it is the iSWAP gate. You do this by bringing two transmon to resonance, and then they will interact. And you can imagine, I just solve this circuit, I will get this. Right? So I'm rushing a little bit. If you have a question, let me know. I will stop here. Any question? Yeah. And feel free to leave. Yeah. No. Actually, I don't know, but probably not. Because when we solve this, we solve this like a simple harmonic oscillator. They don't have the same basis state, right? Okay, any question from online? If not, I will stop sharing.